Okay, now we're recording. So we're going to, and thank you for the reminder. So we are going to talk about our final topic. And again, we're going to kind of be brief about it because there's a lot that's similar. But I just sort of want to give you some context and talk about what it looks like. And like I said, I'm not expecting this to be terribly long. So diffraction is our final topic, and we will see that some interesting waves, as we've seen, are they're very interesting because even classical waves are very non-intuitive and they're not local, right? If you're having a hard time picturing electromagnetic waves or optical waves, just remember that mechanical waves, like ocean waves, like the ones we studied at the very beginning of the semester, actually have these same properties. And we discussed some of these properties in the beginning of the semester, okay? One of the more interesting and very counterintuitive properties of waves is that they're not really local in space. What I mean by that is if you look at a picture of the ocean, right, you'll see these large waves that sort of move onto the shoreline like this. You can't describe that wave as being at any one place, right? It's all over the place. It's a long object that moves. It's non-localized. Because a lot of people say like, oh, it's hard to picture wave motion. But we see wave motion all the time. It's hard to process it in terms of the normal motion, particle motion that we're used to. And that's where things get weird. But when you have barriers in waves and waves can interact with things, that's when things get interesting. And we actually saw examples of diffraction when, well, we might not have, because I forgot we went online very quickly. But if we, I don't know if we did the example in the sound wave where what I typically do is I go outside of the classroom, and you can do this or have one of your little siblings do it. It'll give them an opportunity to scream. And I talk loudly with the door closed, and then I open the door slightly and talk right, aim the sound waves at the door and at the crack in the door. And you'll notice if you talk at that crack, the volume becomes much more audible. And that's what you're seeing there is diffraction, is that little crack acts as a source, a new source for the wave, and it can expand out spherically, and that's why it appears louder. So what we're going to talk about is we talked previously, right, about the double slit experiment, and I wanted to do some drawing there so we can sort of review what we looked at. And with the double slit experiment, we talked about wave fronts, and we talked about interference. All right, so let's review those concepts very quickly. So basically, there's our slit. We're going to make our screen black, because why not? So our screen is large and will take up the whole page. All right. I'm going to move these to make them a little more symmetric because I can. I'm going to move this to make it a little more symmetric because I can. It's okay. It's not great, but it's not terrible. Okay, it's not capital T terrible. It's still pretty bad. So let's go here and change colors again, and we're going to use red for our incident waves. And those are going to look like plane waves. Remember that. If you're far enough from the source, these look like plane waves. And what happens is a lot of the wave gets absorbed or reflected here, but at the slit, right, we have new secondary waves. So I'm going to try and draw these. Even in class, I'm pretty terrible at drawing these. That's okay. No, my stylus. Dropped. So let's take a look at our waves from our new source as they go out. We'll just kind of do the best we can. So wave 1 will look like this. It'll come out in half circles. And it'll expand like so. And then we'll get a secondary wave. You'll notice we start to get some interference patterns, right, where these cross. And when we look at the screen, I'll pick purple, or I'll pick green. We'll get an interference pattern, right? We'll get fringes that'll be bright, dark, bright, dark, bright, dark, bright, dark, all up through the screen and in the same pattern. Okay, and this is our classical interference pattern for our wave. All right, and this is an indicator of wave properties. So what I want you to understand, this is a good time, is pretend if we didn't have, if light wasn't a wave, like if you shot particles through here, the particles could only go through each of the slits, and they'd only go through one at a time. You wouldn't have simultaneous new wave fronts, right? So imagine if instead of waves you had a machine gun, and you were firing bullets through the hole. You would have a bullet pattern that looked a little like this from each individual slit. You'd have a sort of this Gaussian distribution on each slit, and then the overall distribution would look something like, we'll use green again, but for particles you'd have something that looks like, we'll use orange, whatever, something that looks like this, right? And you wouldn't see anything over here because that would be out of the angle for which the bullet could leave these slits, right? That would be limiting. And so you'd only get bullets distributed in this area. So Young's double slit experiment is important because it lets you sort of fundamentally and very powerfully answer whether a phenomena is wave-like or particle-like. And this is where if you moved on to quantum physics, we would revisit this and talk about the condition in which we get particle-like behavior and wave-like behavior. And this is the central process behind wave-particle duality, the central experiment behind wave-particle duality. It's very interesting. So, but we want to talk about interesting thing that happens when a wave diffracts. So with single slit diffraction, you have one slit, right? And you'll notice that the same arguments that we look at can be made, that sort of be made arbitrarily small at a point, right? We can break it up into arrays from the single slit. These integer arrays, and you can get an idea of how much you can break up this wave in by understanding the wavelength, right? So A can't be continuously broken down. I mean, you have to have an integer numbers that are on the scale of the wavelength, and that will give you an idea of the diffraction minimums or maximums here, right? These aren't interference minimums or maximums; these are diffraction minimums or maximums. All right, and again, some of the criteria we need to be on. Our A would be, it's helpful if it's on the scale of our wavelength. And of course, we should have stated this before, but the interference patterns we look at are something called far field effects. So that means that this D, this distance, big D, has to be much greater than A. So the screen has to be very far away from the slit. So this is, of course, not to scale. So usually, if we're talking about the wavelength of light, we'll be in the millimeters at most, or microns, things like that. And then here, we would be in the meters, right? We'd be meters away. So let's see what a diffraction pattern actually looks like. That's the next thing we want to look at. But the criteria, you'll notice, is set up just the same way it was in the last chapter for minimums and maximums, or for maxima. And the maximum, because they won't all be the same width, we have to say are located approximately halfway between the minimum. That's what we're going to find. And we're going to find with diffraction that we usually concentrate on the central minimum. As you can see, the relative intensity goes down very quickly, right, for diffraction. And so we concentrate on the width of this primary pattern. Okay, and you'll notice that you can look at the intensity of the diffraction pattern is given by this expression here, and A alpha is equal to pi A lambda over sine theta. All this, when you're looking at this as far as deriving it, the derivation is very similar to the stuff we did for double slit diffraction and things like that. It's the same kind of process. So you want to become, the conditions for maximum and minimum or constructive or destructive interference look the same, but they are slightly different, which, as you can see here, if you get too far away from theta or from 0, right, for alpha, your intensity is going to peak at 0, and it looks like, and this is one of those things where it looks like it shouldn't, but calculus will sort of give you the idea that it can, right? So this is relative intensity. Again, it looks like it should be 0 here, but then you'd have 0 over 0, so that's undefined, We can't really do that. If you take the limit of sine x over x, you'll find that it's 1, and that's where all this stuff starts to work. Okay, so that's something you should know from calculus, and you can get a general idea of the pattern here. Now, what we have to do, if we look, I wanted to cover this before I go into that section. So now that we've looked at single slit diffraction, I want to cover, we're just covering this in opposite order. We are going to go back to that section, but I want to show you what happens when you combine sort of what we see this chapter, right, our diffraction, with our interference pattern from a double slit. And what you see is that we get this combined interference pattern, right, where we see the where we see our intensity. If our slits are on the order of the wavelength, our intensity sort of dips and gets the single slit diffraction pattern acts as an envelope function, which means that we still have interference here, but it's very limited in intensity, which you can see from these lobes, right? And this should also make sense why we concentrate on the central diffraction pattern. You can actually see that the interesting stuff will happen here, and you still get interference in that central diffraction pattern. If we were in class for the final lab, I would demonstrate this with a laser beam and the Pascal equipment. It's actually pretty easy to do, and I'd have you create the pattern, which you can actually do on your own in lab, could have done, but we're not quite there. So this is what it looks like, and I just want to sort of introduce you to that idea. And you can look here at the full, you'll notice you're sort of combining both things. We saw that the intensity was equal to this cosine beta part here. That's your two-slit interference term, and then your single-slit diffraction term is here. And you'll notice that they are strikingly similar, these angular arguments. One depends on the distance between the slits, and one depends on the width of the slits themselves. All right, but the idea of theta is the same. And again, because you're looking at the same point with respect to the slits. Okay, so that's kind of it for there. I want to look at, I want to go back and talk about resolve circular diffraction by circular aperture. So this is more in line with what we were talking about, but because so we're going back now to a single slit, but instead of a rectangular slit, we're going to a circular aperture. Now, circular apertures are important because for those of you who do photography or any kind of video making or editing, all of the apertures there are circular, right? And so is the aperture for your eye. So diffraction by the circular aperture or a lens with a diameter d produces a central maximum and concentric maxima and minima given by this expression here, and it looks like this. And this is often the easier diffraction to see, these circular apertures. So here, angle theta is from the central axis to any point on that circular minimum, all right? So you'll notice they're sort of evenly spaced out. The main difference here is this 1.22 factor, which just comes from the geometry of it being a circle. But the interesting application to look at here is resolvability, all right? So resolvability is extremely important in image processing. In fact, whether you're looking at a telescope or a car or a TV, right? The ability to differentiate two pixels or two things indicates how much detail you have. And so we have here this Riley criterion, which sort of mathematically tells us that two objects are on the verge of resolvability if the central maximum, if the central diffraction maximum of one is at the first minimum of the other, right? So basically, if object 2's dot is at the first minimum here, then these two things should be resolvable. You'll notice here that it's sort of interesting because it's done very at the limits of resolvability here, but you can actually see with telescopes that as you collect more light, a big sort of bright object like this can resolve into two very tiny points if we're able to really push limits here, or really you have a lot of room to work with. The easiest way to see this is if you look at a car coming from far away, it'll look like one bright dot. And basically, when you're through the circular aperture of your eye, it'll look like this. And then as it gets closer, you'll be able to resolve the two headlights. All right, that's sort of your way to experience resolvability. But you can also see this in artwork. Generally, I'd have the class come forward, but I'd ask you to put your head really close to the monitor. And and you'll notice this painting looks very different between your head being very far away from the painting and very close. And you'll notice that if you look very closely, this painting is created by creating many, many individual points, which you can see. It's a lot of colored dots. So play with that for a minute and, you know, take a look at it. Okay, so hopefully you're back and you've had some fun with that painting, okay? So any questions so far? I'm just gonna get us to our diffraction gratings. That's a really good question. So in modern times, yes, everything you see on a screen absolutely can be. Not everything was designed to be resolved into dots, but I think you can probably get to a point where things do start to pixelate. That's a fundamental. I mean, whether everything. The question fundamentally, right, Chewy, is can everything be resolved into dots? Comes back to this idea of discrete versus continuous, right? If the universe is truly discrete, as quantum theory would tell us, then yes, everything can be resolved into dots eventually, right? And some exotic hypotheses of physics will even state that time and space themselves can be broken into dots. However, there's still people arguing for continuity, which has its problems because the atomic world does not behave in a classically continuous sense. But general relativistically, which is a very well-verified theory, it very much does. So whether things really are all dots or quantized is still being investigated. Quantum theory points to the answer to that question being yes, and in a very powerful way. I don't want it to seem like that's a hypothetical, but the scale at which things become, at the individual photon level, is not an issue I think we would have in perceiving things. An interesting way to sort of look at this without getting too deep into the fundamental physics, there's a video I like to show, which actually I think will make it part of this lecture because we're almost done and we're not even close. So I'm doing an ad hoc activity for everyone to look at, not answer Juie's question, but to think about it. It's a really good question. Let me go to youtube.com. I wish I could share YouTube videos, but it doesn't really let me. Super Mario Brothers at 380. 1000 FPS.
Hello there, my name's Gavin. Welcome to this episode of Cyber Jack's very haunted section of my living room. A while ago,
All right, this video does come with an epilepsy warning, but you can at least start to see how the images that you take for granted every day become dots. So let's watch this video and we'll hopefully that will give you insight. We'll have some questions on that. So I'll turn off my sound so that you can watch the video. I'll be back in about 12 minutes. So pretty interesting, huh? You can sort of see from the resolvability limitations that things that you look at aren't clearly, they're not always what they seem, right? And so that's a probably more effective demonstration of resolvability than just our slides. But looking at how waves, the resolvability of waves, this actually makes me, actually no, I was going to skip it then go through. But looking at how light can interact with many particles, how it can refract or leave from them or scatter off them, gives us all sorts of information and resolvability into smaller systems. All right. So when we talk about a diffraction grating, this is going to be important because right now we have individual gratings, right? We take our double slit and we just say, well, what happens if we put a bunch of little slits here? Now this may seem trivial, and you'll notice that again the criteria for maximum and minimum looks just the same, and we get this half width from the center point where it disappears into darkness is given by this equation here, and that's all nice and good. But what we really want to be able to do is look at patterns caused by diffraction slits. And this is important because if you start to be able to leverage higher wavelengths of light, you can see interesting things. Now, I want to be, or higher frequency, lower wavelength of light. I'm sorry. I got that mixed up. So I guess what I'm trying to say here is we look at the electromagnetic spectrum is interesting and it helps us see, but you'll notice we can't see certain things, right? Like we can't see atoms and we can't see, DNA is barely visible in an optical microscope. You can't really see it. And there's a lot of there are a lot of things in the microscopic world that we can't see with visible light. And that is because you are limited by what you can see by the wavelength of the light itself. So basically, what I'm trying to say here is that if an object is smaller than the wavelength of light, you can't see it. But if you choose something with a smaller wavelength and then can process the image, you can investigate the small scales of the universe. All right? And so even though with light, because remember these slits have to be on the size of the light. So here, if we're in visible light, this is hundreds of nanometers, right? So we're talking like micrometers, millimeter to tenths of millimeters, things like that. However, when we look at and make this bigger, or make the frequency bigger of the wavelength smaller, I'm not going to talk about dispersion and resolving power there. Those slits become the size of atoms. And we can actually use X-ray diffraction to look at the lattice structure of solids. All right, and that gives us a very powerful amount of evidence into investigating the world as substances created from atoms, because we can actually use high energy light and a diffraction pattern to resolve atomic spacings. And this is consistent with our quantum theories, which led us to the very large and important conclusion of modern science that we live in a world of objects made up of atoms. And we know that because we can directly analyze the spacing in any solid with high energy diffraction. And that's just one of many, that's a huge piece of evidence, but that's just one of many, many parts of the evidence. And to sort of wrap up this course, because that's sort of how it ends. You can read the details here if you want, but I wanna sort of springboard you into what would be the next course in physics. So what we've seen here, and what we've done is in Physics 1, you learned about Newton's laws, which was the construction of physics as a theory. And even though you didn't get to thermodynamics, if you take thermo, you'll start to understand that physics at that Physics 1 level is about understanding physics of a particle, of a point, and then understanding it in terms of a solid, liquid, and gas. Right? You do rigid bodies, solids. You do liquids, thermodynamics, or fluid dynamics, and gas. All right? And then here in Physics 2, we expand that into, that covers your particle nature of the universe. Then in waves, or in physics 2, we concentrate on predominantly wave effects. So we talk about optics, mechanical waves, and we develop the electromagnetic theory. Now, the connection here between X-ray diffraction is physics moved in this direction following the 19th century into the discovery and verification of the atomic realm. So for the 20th century, the story is the world of atoms, right? And the properties of atoms and being able to describe these atoms. And the 21st century, once you do all that, is not by any means almost done. I find it hard to believe that anyone of serious scientific background really thought that physics was almost done. I know there's a famous saying of that, but physics had some huge problems by the mid-19th century that needed to be solved. And it's not clear to me how any real physicist couldn't be like, oh my God, unless they were just in denial about a lot of it. But looking at the 20th century opened up the physics of the very small, which is the next logical progression for what we're talking about. But it also opened up the physics of the very fast and the very large scale of the universe. And so the 21st century has been about making more precise measurements in these fields of cosmology and expanding our understanding of the quantum. And the attempt is beginning, and been very unsuccessful so far, to reconcile the differences between general relativity at the large scale and quantum physics at the small scale. So you are now ready to branch off into the beginnings of 20th century physics and really look at that stuff. That being said, this stuff doesn't get erased by 20th century physics. It gets expanded upon and refined. So it's not that all the knowledge is useless. It just it carries on a new context. Okay? So I think that's all I have for today. If you have any questions or want to discuss the video or anything like that, that's fine. But I think I'm going to stop recording. I've got nothing more to say. Keep in mind of your important dates of your final. So I'll stop recording.